let's try to unpack this. Imagine, just for a second, everything we can actually see out there.
All the stars, the galaxies.
Right, even us. It adds up to less than, what, 5% of the universe?
That's the current estimate, yeah. Less than 5% is ordinary visible matter.
But here's where it gets really mind-bending. Astronomers figure that something like 85% of the universe's mass is invisible.
Something we call dark matter. Exactly. Though, just to be precise, when you look at the total energy density of the universe, dark matter is about 27%. Ordinary matter is that tiny slice under 5%.
Okay, 27% then.
Yeah.
Still huge.
Yeah.
It's like this cosmic mystery substance, right?
Yeah.
The invisible glue holding things together.
That's a good way to put it. And the fact it's still invisible, still eluding us after all this searching, that's making scientists really question some fundamental ideas about matter itself.
It really makes you think. So in this deep dive, we're basically going on a cosmic detective hunt.
Following the clues.
Yeah. We'll look at the evidence why we even think dark matter exists, spinning galaxies, bent light.
The cosmic microwave background.
Right. And then we'll follow the scientists on their global treasure hunt. These huge underground labs, space telescopes.
Even particle colliders.
And we'll even touch on that really radical idea. Maybe it's not missing stuff. Maybe it's gravity itself that's different.
It's definitely an alternative viewpoint some people are exploring.
So, okay, where do we start? What's the most powerful clue we have?
I'd say galactic rotation curves are still the classic, most compelling piece of evidence. Think about stars way out at the edge of a spiral galaxy.
Okay.
They're orbiting way too fast, much faster than they should be if the only gravity pulling on them comes from the stars and gas we can actually see.
So without some extra invisible mass providing more gravity.
The galaxies would literally fly apart. Those outer stars would just be flung off into space. So this dark matter forms a kind of invisible halo, providing the extra gravitational grip.
Wow, okay. So it's literally holding galaxies together. But it's not just the spinning, is it? You mentioned light bending.
Gravitational lensing, yeah. It's another really strong line of evidence. Einstein told us that mass warps space-time, right?
Uh-huh. And light follows that warped path.
Exactly. So when we look at distant galaxies, sometimes the light passes through a massive galaxy cluster on its way to us. The gravity of that cluster bends the light, distorting the images of the background galaxies.
Like looking through the bottom of a wine glass.
Sort of, yeah. And the key thing is the amount of bending, the amount of distortion we see is far, far greater than what you'd expect just from the visible stars and gas in the cluster.
Meaning there has to be a lot more mass there that we can't see.
Precisely. Vast amounts of invisible dark matter. And then there's the CMB, the cosmic microwave background.
The afterglow of the Big Bang.
That faint radiation from the very early universe. It's incredibly uniform, but there are tiny temperature fluctuations, tiny ripples. Well, the specific pattern of those ripples, how big they are at different scales, only makes sense if dark matter was already clumping together gravitationally before ordinary matter could. It acted like a gravitational scaffold.
So it seeded the structure we see today.
Wow.
Okay, so the clues are strong, very strong. But how on earth do you actually find something invisible? What's the hunt look like?
It's a massive effort, really, on multiple fronts. Deep underground, you've got these incredibly sensitive detectors. Experiments like LUX Zeppelin in the US or Xenon in Italy.
Why underground?
To shield them from cosmic rays and other background radiation that could fake a signal, these detectors are often huge tanks filled with incredibly pure liquid xenon or argon.
And they're just waiting.
Pretty much. They're waiting for a hypothetical dark matter particle, maybe something called a wimpy weakly interacting massive particle to drift through the Earth and just happen to bump into one of the xenon nuclei.
Like a tiny cosmic billiard ball collision.
A very, very gentle one. It would cause a minuscule flash of light or release a few electrons that the sensors can pick up. It's painstaking work.
I bet. And what about trying to make dark matter? Particle accelerators.
That's the other big approach. At places like the Large Hadron Collider, they smash particles together at incredible energies, looking for missing energy or momentum. If you collide known particles and the energy or momentum after the collision doesn't add up, it could mean some energy was carried away by invisible particles, maybe dark matter particles that just fly out of the detector without interacting.
Indirect detection, then.
Exactly. And then there's the astrophysical search, using telescopes both on the ground and in space.
How does that work? Are they looking for the particles themselves?
Not directly. They're looking for the products of dark matter interacting with itself. For example, if two dark matter particles were to annihilate each other, maybe in the dense center of our galaxy, they could produce high-energy photons, like gamma rays, that our telescopes could detect.
Ah, okay. So, searching for the faint glow from dark matter annihilation or decay. Has anything turned up?
Well, that's the frustrating part. Experiments like LUX Zeppelin and Xenon have become incredibly sensitive. They've ruled out huge chunks of the parameter space where we thought WIMPs, especially heavier ones, might be hiding.
So no detection yet. But ruling things out is still progress, scientifically speaking.
Absolutely. It narrows the search. It tells us maybe WIMPs aren't the whole story, or maybe they're lighter or interact even more weakly than we thought, or maybe dark matter is something else entirely, like axions.
Right. What about the big space missions? James Webb, DESI, Euclid, are they shedding new light?
Definitely. Webb is peering back at the earliest galaxies. Seeing how they formed and clustered so early on provides really compelling evidence that dark matter had to be there first, creating those gravitational wells for ordinary matter to fall into.
So confirming that scaffolding idea.
Exactly. And DESI, the dark energy spectroscopic instrument, it's mapping millions of galaxies with incredible precision. How they clump together on large scales, that pattern fits the standard dark matter model beautifully.
And Euclid, and the upcoming Roman telescope.
They're all about mapping the dark universe using gravitational lensing on a massive scale. They'll map the distribution of dark matter by looking at the tiny distortions it causes in the shapes of countless distant galaxies. It's giving us an unprecedented map of this invisible structure.
The evidence keeps mounting. But let's circle back to that alternative idea. What if it's not dark matter, but gravity?
Right. Modified Newtonian dynamics, or MOND, is the most well-known example. The idea is that maybe Newton's and Einstein's laws of gravity are extremely accurate, where we can test them easily, like in the solar system. But perhaps gravity behaves differently over vast cosmic distances, or in regions where the gravitational field is extremely weak, like the outskirts of galaxies.
So you wouldn't need extra matter to explain why those stars orbit so fast. The law of gravity itself would change.
That's the core idea. Proponents argue MOND can explain galactic rotation curves very well without invoking dark matter at all.
That's a fundamental challenge to Einstein, isn't it?
It is. It's a huge deal. The challenge for MOND, though, has always been explaining all this evidence, especially things like the bullet cluster, where you see lensing separated from visible matter and those patterns in the cosmic microwave background. Dark matter just seems to provide a more consistent explanation across all these different scales.
So dark matter is still the front runner, but the debate isn't totally over until we actually find it.
Precisely. The lack of direct detection keeps the door open, however slightly, for these alternative gravity theories.
Okay, so let's try and sum this up. We've got powerful clues, galaxies spinning too fast, light bending strangely, echoes from the Big Bang.
All pointing towards this invisible substance, dark matter.
And this massive global hunt is underway. Deep mines, particle colliders, powerful telescopes.
All pushing the boundaries of technology, ruling out possibilities, even if the ultimate prize remains elusive.
And we've even considered that maybe, just maybe, our understanding of gravity itself needs a tweak.
Which is a fascinating, though still less favored possibility.
But the bottom line is, this stuff, whatever it is, making up roughly 27% of the universe's energy density,
continues to hide. We've ruled out many candidates, but no smoking gun. Yet the search itself is teaching us so much.
It really is profound.
Yeah.
This isn't just about finding some new particle, is it? It feels bigger.
It's about understanding the fundamental constituents of our universe, unlocking one of the biggest remaining mysteries in cosmology.
And it really leaves you wondering, what are we on the verge of discovering here? Is it a whole new type of matter? Some kind of unknown field permeating space? Or maybe even a whole new law of nature?
Whatever the answer, finding it will undoubtedly reshape our entire understanding of the cosmos. The chase is still on.
And every experiment, every observation gets us just a little bit closer to grasping those invisible threads that hold everything together.